So monotonic and bounded sequences are properties that your sequence could have. So these two words are words that I'll use when my sequence will satisfy a certain property. So let's talk about monotonic sequences first. So a monotonic sequence is a sequence that behaves in a specific way. So I can think about it as something that's monotonous, boring. It does the same thing over and over again. So one of the ways in which the sequence can do that is by being increasing. So if you have a sequence and you go plot it, like 1, 2, 3, like this, and you plot your A1, your A2 gets a little bigger, your A3 gets maybe just let's say a lot bigger, like this. So if that keeps happening over and over again, the A's get bigger and bigger, then that means your sequence is increasing, and then you can also use the word monotonic to refer to that sequence. Likewise, if your A's, the terms of your sequence, get smaller and smaller over time as n progresses, let's say 1, 2, 3, 4, I don't know, then maybe your sequence, your A1 is here, maybe your A2 is here, maybe your A3 goes down here, and then the A4 doesn't go as far down but still goes down. Then following the movement of the sequence, it keeps going down forever. That is a decreasing sequence. Another set of words that you can use are the following. You can say that a sequence is non-decreasing. I'll use this sometimes when necessary, but a sequence is going to be non-decreasing when it is increasing at times, but at times it's allowed to stay constant. So it stays constant for a while, but then goes back to increasing, and then maybe stays constant a little longer, but then goes back to increasing. As long as it doesn't ever go down, this is not allowed for a non-decreasing, as the word says, right? You're not supposed to ever go down for a non-decreasing sequence. As long as you go up a few times and stay still a few times, then you'll have a non-decreasing sequence. And likewise, a non-increasing sequence will show up when you have a sequence that goes down a few times, but maybe stays still a few times, and maybe goes down a few times, maybe stays still a few times, and so on. As long as it never goes up, it will be non-increasing, okay? Algebraically, this is saying that an plus 1 is bigger than an. So the next term, the term that comes after an, is bigger. So you just imagine plugging in certain n value. So when n equals 2, this is saying that a2 is less than a3. When n equals 3, this is saying that a3 is less than a4. And then when n equals 4, a4 is going to be less than a5. So for all n, we're going to have this behavior here that I'm describing. And if you look at the algebra here, you're going to see the exact same behavior, except on the last two here, you're going to be seeing that some of those terms are allowed to equal each other. Even if a sequence stays the same all the time, it will be both non-increasing and non-decreasing. In fact, that's the only sequence that's both non-increasing and non-decreasing at the same time. That will be a constant sequence, a sequence that's always the same number. So 3, 3, 3, 3, 3, or 5, 5, 5, 5, 5, or something like that. So in any of those cases, we're going to say that your sequence is monotonic. If any of those four possibilities holds, then you're going to say your sequence is monotonic. Now, if I'm given this example right here, and I want to show that this sequence here is monotonic, what I want to show is one of these four possibilities. So just by looking at this, if I stop to think for a second, I can see that negative 4 over n plus 7. Forget about this negative for a second. Get rid of it. Just think about the fraction. As n becomes bigger and bigger, 4 is being divided by a bigger and bigger number. So the result is getting smaller and smaller. So it will be something that goes down. But now adding the negative to the equation, this is going to be reversed. So it is instead going to be going up and up and up from below the x-axis like this. So it's going to be approaching 0, right? So I do think looking at it, that the sequence is increasing. But I still have to show it. I still have to do some calculations that show that this is in fact true. So I'm going to do this. What I want is to show that an, again, I think it is increasing. So I want to show that an is less than an plus 1. I don't know if this is true. So whenever I have something like this, I use this symbol right here. If you've never seen it before, this is an equivalence symbol. Sometimes you also read this as if and only if, meaning that this on the left is true. If and only if this on the right that I'm going to write still is going to be true as well. So this being true is the same as this being true. I'm not necessarily saying that this is true. I'm saying that if it is true, then this is true, and vice versa. If this on the right is true, then this one also is true. So the reason why I'm doing that is because I don't know if what I'm writing is correct. I don't know if that is correct yet. But hopefully I'm going to start by saying that it is, and hopefully I'll get to the end to a situation, to an expression that I know is obviously correct. So what I want to write is an, that is an right here, less than an plus 1 is just me taking n plus 1 and plugging in to the original sequence. So that will be 4 n plus 1 plus 7. So basically all I did was replace n plus 1 into n here in my original sequence. So the left is equivalent to what's on the right, which is then in turn equivalent to, so what do I do with this inequality? I can multiply both sides by -1. When I do that, I revert the inequality. So n plus 8 like this, because n plus 1 plus 7 is n plus 8. And now I get to take this number, multiply over on that side. This is a positive number because n is a natural number, and n plus 8 is going to be positive. So when I multiply this over, nothing happens to this inequality. And when I multiply this over on the other side, nothing's going to happen to the inequality either. So 4 times n plus 8 is going to be greater than 4n plus 7. I get to cross multiply or use distributive property here actually, sorry about that, for n plus, and then 4 times 8 is 1632, greater than 4n plus 4 times 7 is 1428. Subtract 4n on both sides, 32 greater than 28. Is that true? Yes, it is. I know 32 is greater than 28, and since this is equivalent to this, which is equivalent to this, which is equivalent to this, this means that this can only be true if this is also true, right? I've only applied legal, reversible, mathematical moves here, basically. All of those operations that I've done here are invertible. I can undo them and remain and keep the expressions being true. So if I arrived at a true inequality, that means I started with a true inequality to begin with. And so we can say that an is, so the an plus 1 got bigger, which means it is increasing, which means it's also monotonic. All right. There's a different way to do this. Let me see if I have space. I think I can do this, but maybe I'll do it on the next one. Yeah. Let's look at this one. Let's look at the sequence n over n squared plus 1 as being decreasing. That definitely can be proven in the same way that I just proved the previous example, but I'll do it differently this time just so you can see what can be done. So if you can think of the sequence, or rather of the function f of x as n over n squared plus 1, excuse me, I'm using x now, right? So it would be x over x squared plus 1. We can see that an is the same as f of n. For any natural number that you plug into f of x, you're going to get an, the nth term of that sequence. And so if you can prove that the function itself is decreasing, the sequence will always also be decreasing. And if you're taking this class, if you're seeing this content after taking Calculus 1, you will also realize that you can show that a function is decreasing by taking its derivative and checking that the derivative is negative. So let's take the derivative is 0 of f, sorry. Let's take the derivative of f. F prime of x will be, that will be the quotient rule, so the derivative of the first times the second minus the first times the derivative of the second, all of that divided by the second squared. And so that will be 1 times x squared plus 1 minus x times 2x, all of that divided by x squared plus 1 squared. So I'm going to be handling this. And so x squared plus x minus 2x squared, that will be x squared plus 1. All of that divided by x squared plus 1 squared, and that will be negative x squared plus 1. All of that over x squared plus 1 squared. So as you can see here, the derivative of this function, is negative for all x's in this interval as long as x is greater than 1. As long as x is greater than 1, then x squared is going to be bigger than 1 as well. And when you do 1 minus x squared, you'll end up with a negative here on the top of the fraction. And the bottom is something squared, which is positive anyways. So just the negative at the top dominates the behavior of the function, which means then that this function is decreasing. So this shows that f is decreasing for in this interval. And since the sequence an only cares about values of n starting at 1, we can conclude the same for the sequence an. So you can think about this graphically as you're first plotting your function, something like this, starting at 1, and it's going down forever. And the function is decreasing, because of calculus. And if you were to plot your sequence instead, it would be just a bunch of points on top of that line. If the line itself, the curve itself is going down, then we have no choice but to have the points themselves to go down as well. So this is a nice way that I like to use to prove sequences are decreasing whenever I see that it's easily derivable. Note as well that I had an open interval at 1. If I happened to not have this derivative negative starting at 1, maybe starting at 3 or something, let's say the sequence was, or the function was not decreasing for a while, and then after 3 it became decreasing, then that's also okay. That's also a type of sequence that I know how to handle and that I like. And I say this is an eventually decreasing, in the case that I'm talking about here, sequence. So if my sequence isn't necessarily decreasing, but it becomes decreasing later on after a certain number of terms, I will say that it is eventually decreasing or eventually increasing or eventually non-decreasing or eventually non-increasing, all the same ideas as before. This is not standard nomenclature. This is something that I've made up, and I hope it catches on, because I think this is a very good way to talk about this, very concise ways to talk about this idea. And I will say also that this sequence is eventually monotonic if one of those four things happens. If it's either eventually increasing, eventually decreasing, eventually non-decreasing, or eventually non-increasing. So as an example right here, you can see that this sequence of mine, if I talk about cosine of pi n, get a little closer, you can see, I can plug in a1. So n being 1 is n less than 123, of course. And so I'm calculating the cosine of pi times 1, and the cosine of pi is -1. So a2, though, is going to be the cosine of 2 pi. So n equals to 2. N is still less than 123. And so that'll be the cosine of 2 pi, which will be 1. So right now, the sequence increased from one term to the next. And so a3, however, is going to be the cosine of 3 pi, which will be again -1. So the sequence increased first and then decreased again. So this is not increasing all the time, and it's not decreasing all the time. When I use those words, I'm always talking about what the sequence does all the time when I use those words without any qualifiers. However, and this is going to stay happening, it's going to keep happening all the way to a122, the 122nd term of this sequence. It will be the cosine of 122 pi, which is an even multiple of pi, and so that means we have a whole amount of rotations around the unit circle. So this is 1 again. But starting after this point, what will happen? The sequence will now be 1 over n. So a123 will be 1 over 123. A124 is 1 over 124. A125 is 1 over 125. So you can see that something more predictable is happening after this. The denominators are getting bigger, and so the overall fraction, is getting smaller and smaller. And this means then that the sequence becomes decreasing afterwards. So I will say that it is eventually decreasing. Okay, this is wording that I use, and I think it's helpful. All right, the last idea that I want to talk to you about today is the idea of a bounded sequence. So whenever a sequence has a certain number that it's never below, so the sequence is always above that specific number, we say that the sequence is bounded below. So if you were to graph this, so let's say, let me actually use the grid that I have. So this is 1, 2, 3, 4, 5. And let's say there's a certain m value here. Whenever I plot my sequence, let's say this is a1, maybe this is a2, and maybe the sequence goes up, and maybe it goes down. Doesn't matter. This is a separate concept from monotonic. Bounded is completely separate. As long as all my points are above this horizontal line at the height of m here, and that means that this sequence, is bounded below. So we say it's bounded below, bounded from below, or bounded below. Okay. Likewise, you can have this other number let's say maybe n above here. Let's say like an n. And then your sequence now is going to stay underneath. So maybe this is a1, this is a2. Maybe it goes down forever. I don't know. Maybe it goes up once, I don't know, and then maybe it goes down forever. It doesn't matter. As long as it never crosses above this n line here, then it will be satisfying this inequality, and so it will be bounded from above or bounded above. Okay, and the bounded below is the other one. These are just names that we use to describe our sequences, and if both of these happen at the same time, then we say that the sequence is bounded. If I say that the sequence is bounded without any qualifiers, then that means both of these things happen. So I have an m height and an n height, and my sequence points are sort of forced to stay in between these. It doesn't have to converge necessarily, but it needs to stay in between these values, m and n. Right? So this is just a name that you have to remember, that bounded sequences are sequences that have these numbers that limit them. This number sometimes is given a name, and this number sometimes also is given a name. So this number m is called a lower bound for the sequence, and this number n is called an upper bound for the sequence. There isn't, if the sequence is bounded below, there isn't only one lower bound. I can just get something slightly lower, for example, and that's also going to be another lower bound, or something slightly lower even. Sometimes there's importance in discussing the best upper bound or the best lower bound in some sense. We're not going to be talking about that right now too much. For me, I'm happy that you understand, if you understand these ideas. Now, here's an example. Can you show that the sequence is bounded? So by the way that it's phrased, I have to show that it's both bounded from above or bounded above and bounded below. So very simply, 1 plus cosine pi n over n squared plus 1 is always greater than 1 minus 1 n squared plus 1, because the sequence that includes the cosine can never be less than -1. So the least this could possibly be would be when this is -1, and when that happens, these are going to cancel, and this is just going to be 0 over n squared plus 1, which is 0. So the sequence is bounded below, and on the other hand, I can also say that my sequence is less than 1 plus 1 over n squared plus 1, which is 2 over n squared plus 1, which is in particular less than 2. I'm dividing 2 by something. This something is bigger than 1 because it's 1 plus a square plus a positive. So this is going to be less than 2. It's in particular less than 1 as well, because when n equals 1 is the smallest this denominator could be. So I'll get 2 divided by 2 equals 1, but it's also always less than 2. So I don't always have to choose the best possible upper bound, but you can if you want to. So this would be a lower bound of 0, and this would be an upper bound, which shows that an is bounded above as well. Now it's important to pay attention that this can help you prove that the sequence converges if you need to. Such as by using the squeeze theorem. You see the sequence is greater than 0, but it's also less than this if I stop before getting the number 2. It's less than this. And the limit of this when n goes to infinity equals 0. So by the squeeze theorem, my sequence will converge. So this does help proving that the squeeze limit, that the sequence converges to 0 by the squeeze theorem. But this is not an upper bound for my function, for my sequence, because this sequence, this is not a number, right? This that's circled in red right here is not a number, so it's not an upper bound. An upper bound needs to be a number, so it needs to be rid of all n's, all variables. One last thing I want to mention, which I think is very interesting, is what's called the monotonic sequence theorem. Whenever you have a sequence that's increasing and bounded above, so again, plot this, graph this to understand the idea. Imagine you have your sequence that's A1, and maybe that's A2, A3. It keeps going up, right? So that it's increasing. But let's say also that it's bounded above. So there is this number at the top, maybe call it n, that the sequence can never cross. It needs to keep going up, but it has a point that a height that it can never cross. So it's got no choice but to converge. It needs to approach a specific number, gets closer and closer to that number. That number does not have to be n, right? In my graph, it seems like it is, but maybe you were given the wrong value here. Maybe you were given n plus 1 or something. Maybe you're given a bigger value. Maybe, I don't know, maybe 1,000. Yeah, just to be clear. It's a bigger number right there that is also an upper bound, but it's not what the sequence converges, because there won't be any points, not what the sequence converges to, because there won't be any points of the sequence in this band here. You don't know where it converges to, but you know that it does converge. And likewise, if your sequence is decreasing, you can reach the same conclusion. If your sequence is decreasing, but now it needs to be bounded below, then your sequence will converge. And again, you don't know where it converges to, but as long as the points keep going down, and there's this certain height that you can never cross, then you can know for sure that your sequence will converge, to some points. It could be to m, but it could also converge to something slightly higher than m if it stops a little earlier. So you don't know where it converges to, but you know that it does. This is a very, very, very important theorem that we can use to base a lot of our argumentation later in Calculus 3 courses. So it's important to understand its idea. I'm not going to prove it in this video, but there is a very, very formal epsilon and delta proof for this. Last observation I want to make is that this theorem also holds in the following combinations. If your sequence is non-decreasing and bounded above, so even if it doesn't go strictly up all the time, if it stays constant for some time, and then it maybe goes back up, or maybe it stays constant for a long time, as long as it doesn't go down ever and is bounded above, then we still have convergent sequence. Same as if you have non-increasing and bounded below sequence, or eventually non-decreasing bounded above, or eventually non-increasing bounded below. The eventually portion is a little bit more difficult to grasp, but the idea is that when you're talking about convergence of sequences, you don't really care about what happens early in the sequence for the first terms of the sequence. You care about what happens at infinity. So if it eventually becomes non-increasing, or eventually becomes non-decreasing, or eventually increasing, or eventually decreasing, as long as it's matched with the correct upper bound, then you know for sure that it will converge by this theorem as well.